There are 4 ways to find the delta H for a reaction. We've already talked about calorimetry, which is an experimental way to find the delta H for a reaction. There are 3 calculational ways that we can find the delta H for a reaction just by looking at values in a table. By relying on experiments that have been done in the past, we can calculate delta H values for different reactions that we are not personally doing. Those 3 calculational methods are using delta HF values, using Hess's law, and using bond energies. In the rest of this chapter, we're going to talk about each of those 3 calculational methods. Our first way to calculate delta H for a reaction is based on the delta HFs of each of the products and reactants. We would need a table of delta HF values that have been collected for many different substances. If we can look up all of those reactants and products in a table, we can use this equation. We have a general form of the equation that is shorter and applies to all reactions, but may be slightly harder to understand. And then a slightly more specific form, which is an example of the form it could take for a reaction that has 2 reactants and 2 products. Based on the meaning of the first equation, you should be able to modify the second one for a reaction with different numbers of reactants and products. In our general form, delta H has the standard symbol, and RxN stands for reaction. The Greek letter sigma stands for sum, which means we are adding the things after the symbol. N represents the coefficients in the chemical equation. Therefore, sigma n delta HF of products means multiplying the coefficients times the delta HF values for each of the products, and then adding up the resulting values. We would do the same type of calculation for the reactants. Finally, we would subtract the resulting values, doing products minus reactants. We have a generalized equation. Little a big A plus little b big B goes to little c big C plus little d big D. The little letters represent the coefficients, and the big letters are the chemical formulas of each of the reactants and products. Delta H for a reaction is going to be stuff from the product side on the right minus stuff on the reactant side on the left. We're starting out with C and D, and then we're subtracting A and B. We have little c, the coefficient in front of product C, times the delta HF of product C, plus coefficient D times the delta HF of product D. And then we subtract coefficient A times the delta HF of reactant A, plus coefficient B times the delta HF of reactant B. We multiply the delta HF for each of the products by each of the corresponding coefficients and add those up. We multiply the delta HF for each of the reactants by their coefficients and add those up. Then we do products minus reactants. One thing to keep in mind is that the delta HF for elements in their standard form is 0. A substance may not be explicitly listed in a table, but if it's an element in its standard form, let's say oxygen gas or nitrogen gas or zinc solid, then its delta HF would be 0. Essentially, it takes 0 enthalpy to form it because it's the way it's already found in nature. Here's an example of calculating the overall delta H of a reaction based on the delta HF values of each of the parts of the reaction. We're trying to find the delta H for the reaction between nitrous oxide and water to make nitric acid and nitric oxide. We start with the products on the right side of the reaction. Our first product, nitric acid, has a coefficient of 2 in the balanced chemical equation, and its delta HF value from the table is negative 207.4. We multiply those together. We do the same type of calculation for the nitric oxide. The NO has a coefficient of 1 in the balanced chemical equation and 90.2 as its delta HF value. We multiply those together. The results for the nitric acid and the nitric oxide get added together. Then we do the same type of calculation for the reactants, the things on the left side of the arrow. NO2 is the first thing on the left side. It has a coefficient of 3 in the balanced chemical equation and 33.2 as its delta HF value. We multiply those together. The last substance is the water. It has a coefficient of 1 in the equation and a delta HF value of negative 285.8. We multiply those together. We add the resulting values for the NO2 and the H2O. Finally, we do products minus reactants, things on the right side of the reaction minus the things on the left side. We can do the whole calculation in our calculator all at once, as long as we are very, very careful about parentheses. We come out with the negative 138.4 kilojoules per mole. Using the provided delta HF values, calculate the delta H reaction for the following reaction. C6H6 liquid plus 7.5 O2 gas yields 6 CO2 gas plus 3 H2O liquid. C6H6 liquid has a delta HF value of 49.0 kilojoules per mole. CO2 gas has a delta HF value of negative 393.509 kilojoules per mole. H2O liquid has a delta HF value of negative 285.83 kilojoules per mole. Is the answer A, negative 58.7 kilojoules, B, 728.3 kilojoules, C, negative 3,267.5 kilojoules, or D, negative 3,169.5 kilojoules? The correct answer is C, negative 3,267.5 kilojoules. Remember to do products minus reactants, not the other way around. Oxygen has a delta HF value of 0 because it's an element the way we find it in nature, but all the other values were listed in the table. Remember to multiply those by the coefficients of each thing in the balanced chemical equation.